Welcome to this lesson in which we will learn about sequential decay. In the last module, we discussed all about decay and decay types. Let us now have a look at the decay of beryllium-12 to boron-12 by beta- decay. Now you may assume that boron-12 is stable, but in fact, boron-12 decays to carbon-12 by beta- decay. Carbon-12 is stable. Such a decay we call sequential decay, and there could be many decay steps before a stable nuclide is reached. So let's have a look at the simple decay chain in which the first radionuclide decays to the second and then to the third, which is stable. In such cases, we can see that the first radioactive atom disappears with its decay rate. But the second radioactive atom in the chain is being formed by the decay of the first atom, and it decays to the stable atom free at its own decay rate. If we solve the second equation, we get this equation which shows how we can calculate the number of atoms of the second radionuclide in the chain. This equation shows how the production of the second radionuclide depends on the decay constants of both the original and the produced radionuclide. There is also the term shown here which shows the number of atoms of the second radioactive atom at time 0 or at the reference time point. In most of the cases, we assume that there are initially no atoms of the second radioactive atom present, which makes the equation somewhat simpler. We call the relationship between these radionuclides in a sequential decay mother-daughter relationships or parent-progeny relationships. I will stick to the mother-daughter analogy in my lessons. Okay, so we saw the equation that we can use to calculate the number of atoms of the daughter at any time. If we want to determine the activity of the daughter, we need to replace the atoms of the mother and the daughter by their activities, remembering, of course, that the number of radioactive atoms is linked to the activity through the decay constant. Let us use an example to see how we can calculate activities in sequential decay. We have here silicon-32 decaying to phosphorus-32. Silicon-32 has a half-life of 153 years and phosphorus-32 has a half-life of 14.3 days. If the activity of silicon-32 is 100 megabecquerel at time 0, what will be the activity of phosphorus-32 after 100 hours? We assume that at time 0 there are no radioactive phosphorus-32 atoms present. To calculate the activity, we use the equation we just discussed. We first calculate the decay constants. The decay constant of the mother silicon-32 is calculated by dividing the natural logarithm of 2 by the half-life. Do not forget to convert the half-life into seconds. This results in 4.83 times 10 to the power of 9 seconds, which then in turn gives the decay constant that is equal to 1.44 times 10 to the power of minus 10 per second. We can now calculate the decay constant of phosphorus-32. We first convert the half-life to seconds. This gives 1.24 times 10 to the power of 6 seconds and a decay constant of 5.61 times 10 to the power of minus 7 per second. The activity of silicon is 100 megabecquerel, which is equal to 100 times 10 to the power of 6 becquerel. The time of 100 hours is then converted to seconds by multiplying it by 3600 seconds. Now it is a question of filling in all these values in the activity equation, giving that the activity is equal to 18.2 times 10 to the power of 6 becquerel. Thank you for watching. In the next lesson, we are going to discuss decay equilibria.